Hi there, good to see you again. Today we are going to talk about this technique that is called branch and bound. And we will see this technique is very powerful to solve some types of problems, um, interesting problems actually. In order to start talking about the technique, we will remember a little bit about optimization problems. And when we are trying to solve a problem like those, basically what we are trying to do is to seek either to minimize or to maximize a given goal or objective function, which usually is subject to a certain number of constraints. And by considering this idea, we can establish the definition of a couple of types of solutions. The first one is going to be called the feasible solution. We are going to have a feasible solution when we find a point in the search space of my problem such that it satisfies all the specifications of the problem. For instance, if I am trying to solve the traveling salesman problem, what I need to do is to find a tour that connects all the cities once in the tour. So any Hamiltonian circuit is a feasible solution for the traveling salesman problem. It doesn't violate any of the constraints. However, not all the Hamiltonian circuits are going to be the optimal solution for the traveling salesman problem. And that is the second definition that we are considering now. We are going to say that we have an optimal solution when we take one of those feasible solutions with the best value that we can reach for the objective function. So again, going back to my example of the traveling salesman problem, we can say that the optimal solution is going to be the shortest Hamiltonian circuit. So we're interested, of course, in exploring mainly feasible solutions, and then among them, we want to find out which one is the best one that we can get. So, moving forward, branch and bound is sometimes compared with backtracking, another technique that we study. But in this case, we will require two additional items in order to work. The first one is a way in which we can provide for every node in this state space tree a bound, a limit on the best value that the objective function, or for that matter, any solution, can be obtained if we add more components to a partially constructed solution that is represented by that particular node in my search tree. So we need to compute this bound, all right? And the second item that we need in the branch and bound strategy is we need to remember what is the value of the best solution that we have seen so far, that we can found so far. So these are going to be the two elements that we are going to need to compute somehow. And we will see how we can do that. And in any case, if we have this information available, then we can compare the bound value in the node that I am exploring with the value of the best solution we have seen so far. If the bound value is not better than the value of the best solution that we have seen so far, then basically what this is telling us is that it's a non-promising path. We are not going to find anything better than what we already have. So in that case, we are not interested in exploring from that node below in the tree. That is why some people say that when we are doing this, what we are doing is like pruning the tree, because we are not interested in going down. So we will stop there, and we will save some computation by not needing to explore below. This is very important because it means that following that path, non-promising path, we cannot obtain anything better than what we already have. And that is the branch part of the algorithm or the strategy. You see, we are talking about branch and bound. So the branch is to try to explore by branching, but we are not going to be branching all the time. Every time we try to branch my tree, to grow the tree, I will check the bound of the new nodes. And if the bound promised by one of those nodes is not better than what I have already, I am not interested in exploring it. If it is promising, then I will continue exploring, meaning I will continue growing the tree. So branch and bound. And this technique is, I would say that it's rather general. It can be applied to many problems. Basically, those problems where the greedy and the dynamic programming may fail. However, it is in general slower than those techniques. So if we can solve my problem by using some other techniques, I will prefer those instead of branch and bound. And only if those are not a good fit for my problem, I may come and use branch and bound. Of course, if I am careful enough when designing my implementation of the branch and bound solution for certain problems, in average, it may run reasonably fast to make it like an alternative to solve problems. And this is basically because in practice, many of those branches are going to be terminated very early while exploring, meaning saving computation time. However, it may happen that we may obtain a very large tree when we face the worst case scenario. And it means that we are going to be particularly interested in considering branch and bound for NP hard problems. And then we will try to design this solution carefully, because in the worst case, the time complexity of this method is still exponential. because it may mean that we will not prune many of the branches, and then the tree is going to continue growing, growing, and growing. And we know that for instance, the blind search techniques, we can explore the whole tree in order to find out the solution, and this may grow very, very fast. So let's be careful about that. Okay, so this is like the general idea of branch and bound and some of the basic definitions, but we want to understand how it works so that we can program it. And as we said, and maybe you may have already imagined, the general idea of branch and bound is to perform a best first search for the optimal solution. So this is interesting because it means that the best includes the need to evaluate the solutions. So we need a way to compute the optimality or the objective function value for each one of the nodes. And then we will use that information in order to search in the space. Also, we may remember that not all of the nodes are going to be expanded, meaning not all of their children are going to be generated. Because what we are going to do is to use a criterion that we will design carefully so that it will guide us on which node we are going to expand. And then we will also need something else to tell us whether we have found the optimal solution to the problem or if we still need to continue exploring. So we need these two aspects or elements in the branch and bound implementation. And in order to explain how it works, we will go to this very common problem that is called the binary or the 0-1 knapsack problem. And in this case, we will consider a knapsack or a backpack that has a certain capacity, W, caps W. And what we are going to do, the problem is to find the most valuable subset of n items that can fit into the knapsack. Every one of the items represented here by the index I has a certain weight represented by lower caps W, and also a value represented by V. And we will compute a ratio that is the value density. That is just the division between the value and the weight. All right. And then what we are going to do is that we are going to arrange the items according to the value density from the one that has the highest value to the smallest value. So this idea, in this diagram, we can see the knapsack. We are representing that it has a maximum weight of 15 kilograms that we can use. And then we have 5 items, each one with a given weight, like this one, 12 kilograms, and a price or a value of 4 pesos or dollars or money units. And we have another one of 2 kilograms and 2 pesos and so on. So This is like the definition of a particular problem. And then what we are interested in finding is which one of these pieces we can take into the knapsack so that the value that we are taking is the highest possible. And we cannot, of course, break the objects. They have to be taken as they are or left in the table. That is why it is called the 0-1 knapsack. Each one of these objects can be leave 0 or taken 1. And so in this case, what we are going to do is that we are going to use a state space 3 as the data structure that is going to help us to solve the problem. And this state space 3 is going to be actually a binary tree. Each item is going to be represented in one of the layers of the binary tree. So the levels of this tree are going to be from 0 in the root all the way to n. Remember that we have n items that we can take into the knapsack. So that is going to be the range of the counter that I will use, or the number of levels that my tree can have at the most, right? The root of my tree is going to be, of course, at level 0, and it will indicate that no items are yet selected. So the knapsack is empty. I haven't taken anything, and we are prepared to start considering which one of the items are going to be put into the knapsack. And this is a convention. What we are going to do now is to create a branch. And since this tree is a binary tree, we will have 2 branches. One of them is going to indicate that we are taking the item, and the other one is going to indicate that we are leaving or excluding the item. It doesn't really matter which one is that, as long as you keep the same convention below when you are expanding or branching the tree. In this case, the slide mentions that the left one is going to be selecting 1, and the right one is going to be excluding 0. Okay. Now, we will need to perform certain bookkeeping. We will record the total weights W and the total value V of the selection in the node that we are exploring. And also we are needing to compute a upper bound that is going to be represented by UB upper bound on the value of any subset that can be obtained by adding 0 or more items to this selection. So we need to compute 3 values, W, V, and UB, right? And we will see how we are going to do that. So W, we said, is going to be the total weight of the items that we have selected so far. So we will just be, every time we choose to put one object into the knapsack, we will add to the former value of W the value of the weight of the item that we are including. And exactly the same is going to happen with B. We will add every time that we choose a new item, the value of that item to whatever value we had so far. We will also have a variable that is going to be called the best, which is going to represent the best value density among the remaining items. You will see all these variables taking values in a moment in an example. But and the definition are very simple. Now, remember that we said that we will need to compute the upper bound value. And that is going to be computed in the following way. The upper bound is going to be the total value that we have obtained so far, plus the multiplication of the remaining weight that I can use in my backpack, multiplied by the density of the best item that I can take in that moment. So basically, consider that I have somehow selected one first item and I put that item into the backpack. As long as I do that, some of these values are going to change. I will have the weight of this item inside the backpack. I have the value of this item. And if, for instance, let me go back to better explain this. So you may remember this backpack of 15 kilograms capacity. And let's suppose that somehow I decided to take this first item that weighs 12 kilograms. And I put the 12 kilograms inside the backpack. Means that I still have room for another 3 kilograms. And then I can choose, for instance, between combinations of the remaining items that are still on the table, okay? But the algorithm is going to help us to decide which one to consider. So this is the upper bound definition. And then by using these values, we are going to branch to the next level of the more promising node. That is the node that has the higher upper bound. And this is basically all we need to solve the problem. And in order to better explain how these values are going to be used, I will solve an example so that it will help you to understand the functioning. And we also need to mention when we are going to stop exploring at the current node in the process. And that will happen when one of these two reasons is true. The first reason is because three reasons. The first one is that the upper bound of the node is not more promising than what we have obtained so far. Every time we consider the expansion or the branching of one node, we compute the upper bound, and the upper bound is telling us what is the most I can expect to obtain by going to that node. And if the most I can obtain is not better than something else that I am promised in another node of the tree, it doesn't make sense because I already have something better, so I will just forget about it. The second reason is because the node violates a constraint. And in this case, the most important constraint is the total weight that I can put into the knapsack. So if at any moment I consider adding an item and the sum of the weights of the items inside the backpack is bigger than caps or upper W, then it violates the constraint, is not longer any feasible solution. So we just forget about that. And the third reason is because we are left with no further choices, because we cannot choose anything else. In that case, then, of course, we will need to stop. All right? So we will be checking these conditions every time. So in order to illustrate this better, let's consider a particular case of the problem where we are told that the maximum weight we can carry is 10 kilograms, and we have 4 items, and the table is telling us for each one of the items what the weight of the item is. So we can see item 1 has 4 kilograms, item 2 has 7 kilograms, and so on. We can know also the value of the item. So this item 1 is worth 40 pesos. This one is, the second one is worth 42 pesos, and so on. And you may remember that we talked about this value density, which is just the division of the value and the weight. And it means basically how much every unit of weight is worth. So every kilogram in the item 1 is worth 10 pesos. And for the second one, every kilogram is worth 6 pesos, and so on. And you may also notice that this table has the items already ordered in relation with the value density from the highest to the lowest. It's just, I mean, this is important, but the numbers can be different, all right? The numbers of the labels, these are just the labels of the items, okay? So in this point, I will change to use my iPad in order to solve the problem by using my pen. Let's go there for a moment. We will move to slide where we have the table. We have the initial conditions, the weight, the maximum weight, the number of items, and the initial weight in the knapsack, which is 0. We haven't shows anything, and the value also is 0, and just the formula to compute the upper bound, so that maybe we still don't memorize it, and we will have it here to help us. Okay, so we have here the problem that we were talking about, and we will start solving it. So we will create the root of our tree, just going to be this first node. Remember, this is going to happen in level 0, and here we will have a total value so far of 0 and a total weight so far of 0. The upper bound is going to be this total value so far, which is 0, plus the maximum weight, which is going to be 10 kilograms, minus the weight that is already carried out in the backpack, which is 0, multiplied by the density of the best item in this table, which is going to be this one. So the best is 10, and the value here is going to be, I will put it below, 10 times 10 is going to be 100. So this is the promise that we are getting by, I mean, this is the best we are promised to obtain in our backpack with these 4 items. It doesn't mean that we can reach it. It's just the best we can do. All right. So, but we haven't chosen everything yet. So we will start expanding or branching our tree. And we said that we will have a binary tree. So let me see, something like that. And we are going to have a choose or leave. Okay. And if I choose to pick the item 1, then the value is going to be updated because it's going to be the 0 plus the value of item 1, which is this one, 40. The weight is going to be what we had, which is 0, plus the weight of item 1, which is 4. And considering that the upper bound is going to be V, which is 40, plus 10, the maximum weight, minus the weight that is remaining. I mean, the weight of the items that I have included already, which is 4, multiplied by the best item remaining. That means 6. I will erase this one. So we have, and that means that now then upper bound is going to be 10 minus 4 is 6, multiplied by 6 is 36, added to 40 is going to be 76. So this value means that if I choose to include the first item in the backpack, I am the best I can do is to obtain a total value of 76 in my backpack. And you can notice how this value is already smaller than the promise that I had in yellow before, which was 100. But this is more realistic because I have already started inserting items into the backpack, okay? But now let's consider the case where we do not include object 1. If I don't include object 1, then the total value is still going to be 0. The total weight is still going to be 0 because I decided not to include the first item. The upper bound, though, is going to be different because this is going to be 0 plus times 10 minus 0. But since I decided not to consider the first item, then the best is going to be obtained with the remaining items that I haven't chosen. That is the best is going to be 6. Remember that, and I will change the color here. Remember that every level of the tree is related with one of the items of the table. So here it was for the item 1, see, here it's going to be for the item 2, and so on. All right. So let's complete this computation. UB here is going to be 60. And now let's compare the values of 76 and 60. 76 is bigger, of course, than 60, meaning that it is better for me. I get a better promise of value if I choose to include item 1 into the knapsack than if I choose to leave it. So I will include it into the knapsack, meaning that this is the node that I will expand. The node which is on my right is not interesting now because it offers me less value than the one that is on the left. Okay, so I will branch this node, and again, we will have, I will put it there, something like that. And then again, I could choose or not the next object in the backpack, which is object or item 2. So if I include item 2 into the knapsack, then the value is going to be what I already had, 40, plus the value. Let me clean the table. So it's going to be the 40 plus the 42, which is the value of the second item, meaning I will get 82 value. And the weight is going to be the 4 that I already had plus the 7 that weights the second item. And I am happy, apparently, because I see that the total value is 82, which is actually even bigger than the 76 that I got in the computation. However, all this joy and happiness cannot be true. Unfortunately, I immediately noticed that the weight is violating the constraint. Remember that W here is 10 and I am getting 11. So unfortunately, this is not a good or a feasible solution. So I have to discard that branch and I will not explore anything below that, right? So goodbye, my dear friend. And let me clean here. And then what we can do is to consider that we are not going to include the second item. So B is going to be 40. W is still 4. But UV is going to be different because now we will have 40, I'm sorry, plus 10 minus 4. But we are now moving to the third item. So the best is going to be 5, meaning that we have here 6 times 5 is 30, and plus 40 is going to be 70. Okay. And so apparently from whatever branches we can explore, 70 is the highest. So I will choose that one. So remember again, up to this point, what we have, well, what the algorithm is telling us is you will pick item 1 into the backpack and you will not pick item 2. And this is the best you can do so far. All right? Okay. I'm happy with that. So let's, oh, sorry, color. So let's consider choosing or not the third item, which is going to be two. So here, if I choose it, B is going to be 40 plus 25, which is 65. The weight is going to be 4 plus 5 is going to be 9. And the upper bound is going to be 65 plus 10 minus 9 times the best, which is going to be this 4. And this is 69. All right. So this is the best I can get if I choose to include the third item into the knapsack. But what if I choose not to? Well, then value is going to be 40, W is going to be 4, that doesn't change, but UB is going to change because it's going to be 40 plus 10 minus 4 times at the best, which is 4. And this means 6. This is 24 plus 24 plus 40. So this is going to be 64. And from the ones that I can see, the nodes that can be branched or expanded, the one with the highest value is choosing the third item. And then we can now, of course, consider choosing or not the last element of the item, right? So choose or not, and I will move everything a little bit up here. Okay. I think I can this thing somewhere else, but I don't know how. Oh, there we go. Okay. So what we can do now is the following. So here, P is going to be 65 plus the value of the fourth element, which is 12. So that is going to be 72. 27. W is going to be 9 plus 3 is going to be 11. Oops. And immediately I notice again, this is not a feasible. I will also non-feasible solution. Same here, non-feasible solution. So by leaving this item, what we can, of course, say is, okay, value is going to be 65, W is going to be 9, and UV is going to be 69, because I have no other item to pick. And since there are no further items to pick, this is going to be the last option that I consider. So my solution, I will in another color, in green, I will put here how in each one of the cases we are considering the knapsack to be. So here is going to have item 1, and here it is empty. Here I have 1 and 2. Here I had 1. I'm sorry. No, that's not true. This is only 1. Yep. Okay, it's just 1 because I decided not to include the second one. And here we have 1 and 3. And here we have 1 and 3. So this is the solution to the problem. Only 2 elements can be stored in the backpack, and the value, the best value that we can get is this one. Is the one that is given by choosing the first item, which is 40, plus the third one, which is 25. That is 65, this one, all right? And this is the solution. As you can see, this is a simple algorithm. The only thing that we need to do is to compute this table or prepare this table. And then every time we move into the expansion of the tree, we're going to be considering one of these 2 options. And depending on the upper bound, we will decide whether to expand or not. And that's it. I hope you enjoyed the algorithm, and then we are ready to program it and to run it in our own problems. Have a good day.